Around the world, there are factories making everything from bikes to biscuits. With mega machines mass-producing and highly skilled workers handcrafting. They are the products we use every day. But have you ever wondered how the finest crystal glasses are made? How the country kitchen staple agar is forged from iron? Or how rubber tennis balls are cooked to order? Well, sit back as we go behind the scenes on the production line. Whatever your tipple, there's something satisfying about drinking from a decent glass. And Dartington Crystal makes some of the finest around.
We started in 1967, so we're 51 years old this year. The process is mesmerising to watch, and very few people can actually do it because it's a very, very special craft.
They hand make over 350,000 pieces a year, including one of their most popular, the dimpled tumbler.
Today you're going to be watching the dimpled double old-fashioned tumbler being made. It's one of the first pieces that we made in 1967. We're still making it today and it's still very popular.
And it all starts with the raw materials.
Well, this is the raw materials that we start with. This is a mix of silica sand, lead oxide, which is red lead, gives it the colour, and some potash and one or two other trace elements.
Each batch contains enough material for a day's production, around 40 tumblers.
It's then charged into the furnaces. It's a speciality in its own right in that, you know, the furnaceman has got the job of starting the process. How he handles the material and how it's loaded into the furnace can determine what the quality of glass is like the next day. Chris is an experienced guy. He knows these furnaces inside out. He's been here for something like 30 years.
It's the red lead oxide that sets crystal apart from ordinary glass. The lead makes crystal glassware stronger, meaning it can be made into thinner, more delicate shapes. It's strong enough to withstand engraving and refracts light better than glass, which is why crystal glassware sparkles. The ingredients are loaded into a clay pot and heated overnight to 1,400 degrees Celsius.
It's melted down overnight. It takes about 12, 14 hours of intense heat to make it a red-hot liquid that then is ready for the guys in the morning to take the first gather and start glass making from.
A team of between 6 and 12 blowers work in unison, all using molten material from the same batch.
When it's in a molten form and suitable for working, the blowers will first of all take a first gather, which is a small amount of crystal on the end of the blowing iron, and they introduce a little bit of air, what we call the first bubble. They're blowing into the gob of glass, and that makes it expand and create a little bubble. And they hold, once they've blown, they hold the thumb over the end of the blowing pipe so that the air can't escape. It has to force the glass out.
The molten glass heats the air trapped inside the bubble, causing it to expand. It pushes the glass out, just like inflating a balloon.
Once we've got the first bubble, it's passed on to another blower.
The first bubbles are gently teased out and expanded. Constant rolling makes sure the soft molten glass doesn't sag. As the first gather is worked, it gains some strength, allowing a larger second gather to be added.
Another layer of glass is gathered from the furnace to make it a bigger piece.
The molten material has to be built up gradually, otherwise it'd just slip off the end of the pipe.
When that's uniform and shaped and smooth, what we call a scoop, it's then blown into the mould. And the mould gives it the outside dimensions, but there's still a lot of hand-eye coordination to make sure that the piece is the right weight, the right thickness. A lot of skill involved just in blowing.
Graphite moulds are used to withstand the gob's 1100 degrees temperature, whilst a blast of water is added to give a perfect finish.
When the red-hot glass goes in there, it contacts the water, turns it into steam, and that means that the actual glass doesn't touch the outside of the mould physically. There's a very minute gap, and that gives it that lovely, glossy, silky, smooth finish. Otherwise, it might stick to the mould, and they continually turn it as they blow it to make sure that it's uniform, round and nothing sticks.
The mould also creates the dimple shape found in the base.
You can see it's a tumbler. The base has got a distinctive dimple in the bottom, which is why it's called a dimple old-fashioned tumbler. But it's still got the bubble or the moil where it's joined to the blowing pipe.
Not for long.
What they're actually doing is taking the glass and cracking it off the blowing iron. They, as you can see if you watch, they apply a little spot of water which creates a thermal shock, a little tap, and it creates a clean break.
They make it look easy, but the team have over 250 years of experience between them.
Oh, I couldn't do it, no, these guys, fortunately this is one of the items that we make quite often, so these guys are very efficient at doing it. They're a very skilled bunch. Obviously we've got some people who've been here 1 or 2 years, and we've got a lot of people that have been here for 20, 30, 40 plus years, so we're very lucky that we've got a very highly skilled workforce and very loyal and good at what they do. Because of the process, they have to be a tight-knit bunch that can work together and get along.
After moulding, the glass is around 500 degrees, way too hot to handle, so the next stage is to gently cool it.
It goes into what we call the leer, which is a temperature-controlled conveyor which tempers the glass. It brings it down to room temperature, from red-hot temperature to room temperature, over a period of time in a controlled way.
The technical term is annealing. This controlled cooling releases any stresses in the glass created during manufacture.
When you take red-hot glass and put it in the atmosphere without any control of the temperature cooling, it would probably just shatter. Eventually, the thermal shock will kick in and the piece would just almost explode. The leer controls the cooling and also provides what we call an element of tempering, so it makes it a stronger product.
It takes around 4 hours for the tumblers to reach the cool end and their first quality control check.
This is the end of the leer where the products can now be handled and inspected for the first time. If there's anything that doesn't meet the required standard, it'll get rejected and thrown away, but it doesn't actually get disposed of. We can take the broken product, recycle that as part of the next batch of raw materials that go into the furnace. We recycle and reuse our broken glass all the time, and we never, unless it's contaminated in some way, it never really gets thrown away.
Crushed recycled glass makes up around 10% of each day's molten batch. For the surviving tumblers, the next stage is to carefully remove the moil without damaging the tumbler.
The tumblers are taken from the end of the leer after inspection, and they come into the finishing room. As we said before, they've still got this bubble or cap called a moil, and the next process is to take that off. Joe's operating what we call the cracking off machine. What this machine does is it scores a very fine line with a diamond tip wheel, and we apply a little bit of heat with a flame jet, and that fractures the glass and creates a nice, clean, sharp cut, so that this bit drops away and is recycled as scrap material, and the rest of the tumbler will go for processing further on in the line. From here it goes on to the next machine, which is the top melting machine, and that melts the top rim so that you get a nice, smooth, safe rim finish. The gas jets take the temperature of the glass up to about nearly 300 degrees, and that's just enough to soften the surface, and it creates that nice, smooth finish. The tumbler is now finished, really, and it comes down to Paul, who's the inspector, who makes the final inspection, applies the back stamp for first quality Dartington crystal and a little brand label. The back stamp's really a mark of true quality. It's the word Dartington etched permanently into the base of the glass. So you've got a very fine sand that's fired under pressure, and that way we know that if anybody comes back to us with a product in the future, if it's got the word Dartington on, and then the product then goes down to the guys on the packing bench, and the boys and girls down there will put it into nice boxes.
Around 10,000 tumblers a year are shipped to customers around the world.
It's made to be used and enjoyed, and whatever you're drinking, it always tastes that little bit better.
Cheers! Vinegar. It's commonly found flavouring our favourite foods, but can also preserve food. has medicinal properties, and even makes a natural cleaner. Sarson's vinegar has been a household name for over 200 years, and they make enough malt vinegar to fill 3 Olympic-sized swimming pools every year. But they don't just make vinegar, they brew it, twice fermenting it before it's aged in wooden vats. The process is a bit like brewing beer, and just like beer, the main ingredient is malted barley.
Barley is the very start of the process for making malt vinegar. We've got about 29 tons of barley in this truck here. We'll have a quick look at it and make sure that the quality's all right. So what we have here is the actual barley grain. What we're looking for is a nice clean grain, which is actually, you know, when you bite it, is a little bit nutty in terms of flavour and still got that barley texture in there. It's fabulous stuff which we take from around the Norfolk area. And it's all red tractor assured in terms of what we bring in. This is one delivery in today, and we usually have about 4 deliveries a week.
The factory uses over 3,000 tons of barley a year. It's stored in these grist cases before being sent to be milled.
Basically, we've got the barley which comes down through the elevations and into this hopper here. Inside, we've got a series of rollers, and those rollers roll together and just gently crack open that grain. Not wanting to dust it like a flour, we just want to gently crack it open so that releases the starch. Now this mill itself is about 60 years old, and again it's part of the tradition and the heritage in terms of how we make vinegar. They actually stopped making these mills around about the 1970s, and these old babies are you know, still quite in demand, and you know, because of their history and their tradition and their reliability in terms of what they do.
Cracking the barley kernels open exposes the starch, which is mashed in these giant steel vats to extract the sugar.
From the mill, we've got this lovely cracked open grain. And what we're doing with that is it comes into these mash tuns here. So the mash tun, very much like in brewing a craft beer, what we do is we fill a bit of water into the bed of the mash. Then the grain comes in. About 10 tons of grain will go in there with about 12,000 litres of water. We'll heat that up to about 65 degrees C. So what we want the grain to do is sort of relax and start to pop open a bit, because that then exposes the starch. And then the enzymes in there will then start to break down the starch, so we get this lovely, sweet, sugary liquid. A bit like making like a Weetabix, you know, with hot milk almost. You're trying to create that sort of texture which is in there.
The mixture simmers for up to 11 hours at 65 degrees. Enough to wreck anyone's Weetabix.
And the good thing is, as well, is all of that grain, we don't waste that. We'll actually send that off, and that'll go off for animal feed as well. So the liquid comes out to the bottom of the mash tun in something which is called an underback, and we'll collect that there, which is nice and sweet, and then on to fermentation.
Just as when making beer, fermentation transforms the sugar released from the barley into alcohol.
We've seen where the sweet wort is coming out of the underbacks from the mash, that lovely sweet liquid, which in the next stage of the process is just right behind me here. So these are the fermentation vessels. So, like I said, vinegar, 2-stage fermentation. This is the first stage. So what we've got here is we've got that sweet, sugary liquid, and what we're doing is we add some yeast to that, and the yeast will work with those sugars, and it will start a fermentation where we'll actually make some alcohol. So in here, we've got about 40,000 litres of this sugary liquid with some yeast, and the alcohol we make, it takes about 6 to 7 days, and in that time, we'll get about a 9% alcohol. So quite a strong brew.
After all the sugar is transformed into alcohol, the team are essentially left with a strong, sweet-tasting beer. Tasty, but not so good on your chips.
Obviously here we're making a really, really nice alcohol, which is actually quite a nice taste and flavour to it, but we obviously don't sell that. We make it into a fabulous vinegar.
More's the pity. After fermenting for up to a week, the alcohol is passed through a centrifuge.
So we've got that lovely bubbly fermented alcohol in there, which has taken 6 to 7 days. Now, it's got yeast still within that, and we need to separate out that yeast as part of the process. So, like, I don't know if your granny or your mum had like a salad spinner where you used to spin it dead fast in your lettuce. So what we've got behind us is a similar sort of thing to that. So we put the liquid into these, what they call separators, spin really, really fast, and then all of the liquid and the yeast get separated, and then the lovely alcohol goes off to these beautiful wooden vats where it sits as a feed for the next stage of the process.
The alcohol is aged in these 40,000-litre vats, made from Siberian oak.
And over a period of time, a bit of the flavour of the wood starts to come out into that vinegar and starts to give it a more smoother and rounder flavour as it goes through the process. If you're making a sherry or a whiskey and you put things into oak casks in that and you leave it for it to mature in that, and it picks on that oak smoked flavour in that. So the vinegar, the alcohol that we've actually got here starts to pick up some of those flavours as part of the process and starts to round it off and make it more smooth.
From here, the alcohol goes on to second stage fermentation. This is where the similarities with brewing beer ends.
This is where the real magic happens, but I'm not an expert in here. I'm going to pass you on to one of our master brewers, Andy, who's the brewery manager, and Andy will take you through in terms of what we're doing.
Well, here, what's happening is this is the second stage fermentation. We've done the alcohol stage. This is where we have an acetifier, where the alcohol turns into acid.
These acetifiers use natural bacteria called acetobacter to convert the alcohol into acetic acid, which is a highly concentrated vinegar. The same process happens when a bottle of wine is left open. The acetifiers contain bales of wood wool made from larch that provides a home for the bacteria to live on and multiply.
We have to keep the bacteria at a good temperature. If we maintain that good temperature, the bacteria in the acetifier will make us vinegar for 6 months, could be 12 months.
The mixture spends 7 days recirculating through the wood wool, giving the bacteria time to work its magic.
We feed them with wort every day. We keep the airflow regulated. We keep the vinegar circulating around the vat. These are maintained and monitored 365 days a year, even Christmas Day, which I have the pleasure of coming in on Christmas Day, Boxing Day and New Year's Day to make sure that the feed is maintained correctly. The family now understand after 10 years of doing this, so I come in at 5 o'clock in the morning, I'm away for 7. Well, someone has got to do it because the vinegar, what everyone wants these days, is traditionally made. And we can only maintain the traditions by manually adjusting the wort feeds, the air and the cooling. And that's how we maintain and keep our tradition alive. These vats are part of our family. We call the acetobacter, we call them little fellas, because if you keep the little fellas happy, they will keep us happy. As long as we maintain them correct conditions, they're happy.
As the bacteria feeds on the alcohol, the strength drops from 9 down to 2%. And after a week, the vinegar is piped to the bottling hall, where it's diluted with fresh spring water.
So we've made the vinegar in the brewery. That now is piped over from the brewery building to this is the bottling hall. So that vinegar comes over, and what we need to do with it is filter it. So it goes through a little bit of filtration to make sure it's nice and bright. Then we heat it up in a pasteurizer to about 65 degrees C so that we kill off the beautiful little bacteria so they don't grow anything in the bottle. It goes through a filler. We then go on to a capper. So we put a little cap on top of it. The bottle then goes round to a labeler, which is behind me. We apply the label. We'll produce about 11,000 bottles per hour, and that equates to about 12 million bottles per year. And that's enough to probably make about 60 million portions of fish and chips. We'll actually check Make sure that it's nice and bright, nice and clear, that the cap's on nice and tight and snug, code's on okay, bottle looks great. Now we've popped that one back on the line and that goes out to our customers.
Delicious. The iconic Aga. Once a staple of farmhouses and country cottages, the stoves are now found in kitchens around the world.
If you talk to any Aga owner, they'll talk to the product as though, as you've just said, it's part of the family.
The cast iron design cooks food by gently radiating heat, which fans claim makes food taste better.
Aga food tastes different. It's a soft, gentle, locks in the goodness, locks in the flavour and makes the food taste better.
Designs combine up to 7 separate ovens with hot plates above. And their enamelled iron construction is built to last a lifetime.
I've had mine now 13 or 14 years. I've had 5 cars in that time.
Originally heated by coal or oil and designed to run 24 hours a day, modern versions use gas and electric to produce heat. Behind the famous farmhouse chic design is some serious engineering. Each Aga takes up to 20 hours to build, all under the watchful eye of manufacturing director Jason Allaway.
This is the very start of the process for manufacturing the Aga cooker. So this is where sheet steel gets delivered into the press shop environment. This sheet steel then in various gauges from 0.9 up to 4 mil. From here it goes to the laser cutter. So this is where the sizing of the product begins.
Steel is used to make the base plate and brackets that will hold the individual ovens in place.
This is our laser cutter. This piece of equipment takes the sheet steel and cuts it into the various components, various sizes and shapes. It cuts to an accuracy of plus or minus 0.1 of a millimetre, which is 4/1000ths of an inch, which is like a human hair. So very, very accurate.
Templates of the steel parts are carefully positioned onto the sheet to minimise wastage when they're cut.
We get the best material yield from using this laser. So the parts are effectively nested on the sheet steel. It's like a jigsaw puzzle.
After the pieces have been cut out, another high-tech bit of kit adds the holes and screw threads used to join them together.
So this is a turret punch press. When I say turret punch press, there are several different tools in a turret that rotate round and are placed on the head of the machine there to cook the part. So it cooks the external parts, pierces the holes, and can actually put thread form in as well. So that would be like an M5 thread.
Ah yes, my personal favourite.
The reason we utilise this technology is because of the flexibility it gives you. To do that manually, manual methods, using press brakes, guillotines, etc., it'd be significant hours compared to a fully programmable turret punch press.
After cutting and punching, it's time for bending.
This part is the base of the Aga. So this has come from the laser cutter. We've applied some tapped holes, some M5, M4 holes, and then this will then go through the process and be CNC bent. And as you can see, the operator behind me is bending the product now on this CNC press brake. Very accurate press brake, and this will run at probably 60 parts an hour.
The computer-controlled press applies up to 100 tons of pressure in precisely the right place to bend the steel without deforming it.
It'll take him approximately a minute to bend this base, and then he'll put it into this stillage behind me, and then that'll transfer onto the next process, which is the paint. This is our paint plant process. So we can see we've got the base behind us that we saw being bent on the CNC press brakes. That will then process through this spray booth, where we'll apply a powder paint that'll adhere to the surface and then go through the oven, come out the other end cured into a textured black finish, which provides corrosion resistance and a nice consistent finish.
But what really sets the Aga apart, and key to the radiant heat cooking their fans rave about, is cast iron. Over 1/2 ton of it goes into the biggest Agas, including the doors, ovens and hot plates. The parts are cast in 2 specialist foundries before heading back to AGA's production line. 95% of the iron comes from recycled material. It's heated to 1,500 degrees before the molten metal is poured into moulds. It's a process that hasn't changed in hundreds of years. The freshly made castings are then left to cool. It's this slow, even release of heat that makes cast iron perfect for making ovens. Once they're cool enough to be handled, they're shipped to the AGA factory, where Jason's team takes over.
The castings get supplied into us from our supplier as raw parts, and then they're placed on these CNC machines to have all the different holes drilled, tapped, milled, etc. to provide datum faces or pivot points. So this particular part, for example, there's a hole there, look, that's been drilled into this dome ring, and that's been drilled to create the pivot point for the hinge. So this will go on top of the auger, and this forms the dome ring for the insulating cover. So this is on the simmering plate and the boiling plate, and that pivots up to cover the plate whilst you're not using it, or it's in up position whilst you are. Neil will rotate around all 3 machines, so you can see he's either loading or machining in the background there, and again this process will run at about 60 an hour.
Once the iron castings have been machined, they're nearly ready to be enamelled. But first, they need shot blasting.
Typically, the shot blast process is where we fire shot at the part. It roughs the surface of the part to create what is then a mechanical key, and that allows the vitreous enamel to adhere. If you were to look at this material under a microscope, it would effectively look like a ploughed field with lots of peaks and troughs to allow that mechanical key.
After shot blasting, the castings are given an undercoat or ground coat before the coloured top coat can be applied.
The parts come from the shot blast. We've got that nice rough textured finish, and Ian's applying the ground coat. So they'll apply this ground coat through the spray. It's a liquid, and he'll spray that to a thickness of anywhere between 200 and 250 micron, which is 0.2 to 0.25 of a millimetre. This is the furnace behind me. So once the ground coat has been applied to the part, it's then dried, and then we fire it. The furnace ramps up the temperature for 20 minutes. It soaks for 20 minutes at 780 degrees, and then slowly ramps down again. It's very hot, I can feel it on the back of my neck now. From here, the part's then cooled and then transferred to the colour process.
For their first 34 years, AGA's only came in cream, but nowadays there's a choice of 17 different colours.
This is a colour being applied to the casting. So we've had the ground coat, and this is a second coat colour. So what we see behind us is a pearl ashes being sprayed. Pearl ash is effectively a light grey, and because it's quite a light colour, it will go into a third coat as well following this.
Applying all these coats can take up to 3 days, but Jason says it's all worth it.
Enamel's a fantastic material to use for an AGA cooker. It's much more durable than paint. It lasts a lot longer, scratch resistance, and from an aesthetic point of view, you get that gloss, look and feel that you'd associate with the AGA.
And behind those enamel doors lies the heart of every AGA, the ovens. Bigger models include up to 7 ovens, each with a fixed temperature designed to do a particular job.
All the ovens are preset heat, so the roasting oven is set at 240 degrees, the baking oven is set at 180 degrees, and the simmering oven is set at 120 degrees. And that's where that flexibility comes in. The boiling plate and the simmering plate, again, are preset at temperatures. And this is where the core of the product starts to come together. The guys behind us, they'll assemble 20 ovens an hour, and they'll work an 8-hour shift. Those ovens weigh approximately 30 kilos each in weight. Each part in itself weighs 6-7 kilos. So when they're assembling throughout the course of a shift, the stamina required is significant. So we also supply mechanical lifting aids to ensure that any real heavy lifting, when the final assembly has been completed, we don't have any pulling on the back, etc. You've got to be physically fit to work in this area. This is for sure. And as you can see, the guys behind us, they are.
But their efforts will be worth it in the end. Because finally, it's time for all the components to start coming together.
This is the start of the assembly process. So everything that we've seen earlier on, the base being manufactured, the ovens being put together, that's all coming together now on the assembly line. So the start of the process is the pallet goes on the assembly line, and then the base gets put on top of the pallet, and then the product starts to come to life. So all the chassis parts come together, you get the simmering oven, the baking oven go on, and the roasting oven surrounded by insulation, and then that follows on to the next operation. So we're about a third of the way down the process. You can see everything's starting to come together. All the assemblies are going onto this cooker, and we've got Andy there putting the divider plate on. So this is where the electrical components are assembled in the oven. So in this particular instance, this is a dual control. So this is the product that can be left on in effectively a slumber mode and then turned on when you need it up to full temperature. And that includes the boiling and the simmering plate, which are effectively the cooking hot plates. Technology's moved on significantly since the old solid fuel-fired products. And now this is a gas-fired product. Our most popular product is an electrically fueled product. That's our DC, our dual control.
Argers are renowned for their quality and durability. The company recently tracked down the oldest working model, an 86-year-old veteran. Little wonder then that before leaving the factory, each one is thoroughly tested.
This is the final stage of the assembly process. So this is the photography area where we're taking a photograph of the front of the appliance and the top. And that photograph can be given to the consumer. It travels with the Arger then for the rest of its life, is linked to the serial number, and that's to ensure that everything is 100% perfect. So when it gets delivered to that consumer's home, they're as happy as we are.
The cooker's then packed. Boy, is it packed. Ready for delivery to the customer. And when it arrives at its new home, there better be a few people to take delivery, because a finished unit can weigh over half a ton.
When you see the quality, the detail that goes into the assembly, the manufacture of these products, you can see that they truly do last a lifetime.
Whether you're an armchair umpire or Grand Slam champion, tennis is a game enjoyed around the world. So much so, an estimated 300 million tennis balls are made each year. Despite the demand, one ball maker is shunning mass production in favour of a time-honoured method. Price of Bath. This small family firm have been making rubber balls for tennis, squash and racquetball for over 80 years.
I've been here 37 years, so I'm hoping to be here for another 20-odd years, but we'll see.
But rather than compete with mass producers in Asia and the Far East, the company specialise in custom-designed balls. It's led by third-generation ball maker Louise Price.
We make about 300,000 tennis balls a year at the moment, but we've got the capacity to scale up or down, so it's supply and demand, really.
Today, the team are making a batch of custom tennis balls for a corporate client. The first job is to mix the raw ingredients, the biggest of which is rubber.
So this is a bale of rubber, natural rubber. This is how it comes into us from our suppliers. Rubber, the natural rubber, come from rubber plantations where it drips out of the trees.
Rubber is what gives tennis balls their bounce.
Ours at the moment comes from Malaysia, but you can purchase from Vietnam and other countries that have plantations.
It's been harvested in the same way for thousands of years.
It's a bit like elastic bands. It's really stretchy. If I was to drop it from a high height, it would bounce uncontrollably. But we can't use it like this. We need to be able to get it into a state to be able to mix into, so it has to be masticated on the mill.
Mastication squashes and stretches the natural rubber, breaking the chemical chains, making it soft and pliable, and turning it a darker colour.
Which turns it into this. Again, still rubbery, very bouncy, but a nice even surface to be able to mix with.
The mastication and mixing happen in this 60-year-old machine, affectionately known as the Beast.
This is a massive machine, 2 big rollers that turn, and it looks old-fashioned, but they still use them today. Ours is an open mill, so it means that you can put anything in from it, from the top and mix in.
Before it can be moulded into shape, up to a dozen other ingredients need to be mixed in.
Each ball has a different formulation. Those formulations consist of rubber, some accelerators, which are the things that make the rubber cook, and a number of other things to help determine the weight and the bounce and structure of the ball.
Competition tennis balls must be a certain size and weight. And crucially, the air-filled ball should offer just the right amount of bounce. That's between 135 and 147 centimetres when dropped from a height of 254 centimetres at sea level at 20 degrees C. All very technical. Thankfully, Louise has a team of pros.
So this is where all those ingredients are in smaller quantities, easy for Andy to access. It's where he weighs out the mixes to get the right measurements for each mix. I mean, each mix is different, you know, whether you're making a regular tennis ball or a children's tennis ball, whether you're making a racket ball or a squash ball.
Back on the Beast, chemical additives are being mixed with the masticated rubber. A chemical accelerator is added, like baking powder for the rubber, that helps it cook once it's formed into the correct shapes. Chemicals like stearic acid and magnesium carbonate are also added to perfect the weight and bounce of the finished balls.
It's quite a lengthy process because it has to be mixed very well to get a consistent ball, consistent performance.
As it's rolled, the mix is gently warmed.
It's pretty hard work, it's physical work, and it's fine-tuned because if he keeps it on the mill too long, it gets too hot. At that point, the rubber can start cooking. When it's finished, Andy sheets it off at a certain thickness when everything's blended in and consistent all the way through. Once it's mixed, it has to come off quickly, get into the racks ready to go on to the next stage.
And the next stage is to divide the mixture into portions called pellets, ready for moulding. The mix is 50 to 60 degrees C when it comes off the mill, and as it cools, it becomes harder to work with, so time is of the essence.
So it gets fed into this machine in a sausage, pushed through with pressure through the hole, and the knife chops it off to the required size and weight that's all set with these measurements. It's a really quick process, comes into the travelator onto here, and that solution's got anti-stick, anti-tack to stop the rubber all sticking together. At the moment the rubber is still warm, so you can chop it up, but the minute it hits the water into the anti-tack, it starts to cool. If you touch the nuggets now, they're still warm to touch, but within a few minutes they've cooled right off. From here we take those pellets to be moulded into half shells.
Each 25-gram pellet contains just the right amount of material to make 1/2 of a ball. The pellets are loaded into a press before they're squeezed into shape.
So this is 1/2 of a tennis ball. Callum behind me is loading up all of them into the press, and it cooks on a 2.5-minute cycle under pressure. It's equivalent of having several lorries on top of you to push the rubber into the right place of the mould, about 200 tonne. And after 2.5 minutes, the shells will come out, and that's half your ball made.
The cooked half balls come out of the oven, moulded into a tray of 36.
Tyrone's about to punch sheets of tennis balls out into the half shell. So then we'll have no flash left, and those two halves can be put together to make a ball. This machine is really noisy, and it's the punch. So they load shells into a knife, goes underneath, and the tonnage just drops on top to punch the shell through. So from here, they go on to the next stage where they get joined. We load a tray with glue, joining solution, which is then loaded with half shells of balls. And once they're in position, they're dipped, so they take a little layer of glue on the rim, and then you'll see Kerry moves them off with air ready to dry, so they're tacky, ready to put two halves together.
Kerry uses a vacuum pump to position a tray of glued halves onto their other halves before storing them in racks, ready to be permanently sealed together.
It's been here a long time, so I'm trying to guess how, 25 years, is it? 24. 24 years. All the members of staff, they're like pieces of the jigsaw, and although they're all very good and can do each other's jobs, their knowledge is tremendous. Having a member of staff that you can rely on is key to everything, really.
To withstand serves that regularly exceed 100 miles an hour, the glue needs to cure, fusing the two halves together.
At the moment, you can pull the tennis balls apart, but once it's been through this machine, it's a solid joint, nice and strong. Chris populates all the areas and then twists the ball so it's loaded in a particular way to make sure we get pressure put around the joint.
The balls are heated to 150 degrees C for 20 minutes. The pressure of the clamp fuses the two halves of the balls together.
We're a steam-powered factory. All the machinery is heated up by steam and cooled down by water. And this is an example of one of those machines behind us. I enjoy hearing the hissing of the valves going and the occasional leaks. It gives you a real feeling of nostalgia.
After cooking, the balls are dropped into a vat of glue, which will eventually help the felt cover stick to the rubber surface.
Now the balls are solutioned, they're ready to go to the coverers, so we need to go and get the cloth sorted, and then these get delivered.
The cloth is a blend of wool and nylon. It's cut from rolls into figure-of-8 shapes, 2 to cover each ball.
The cloth has been cut from its rolls, and Andy is now punching out the figure-of-8s. He's using a fly press to manually punch out 4 strips of cloth at the same time.
The most popular colour, called optic yellow, was developed in 1972 to help TV viewers more easily spot the ball. Up until then, tennis balls were white or black.
In an hour, he can punch 18 blocks, which is 648 balls. From here, this goes into a machine, gets dipped into a rubber solution that allows the two halves of the balls to be stuck together.
And that job falls to the ever-present Andy, one of the firm's longest-serving members of staff.
I'm just going to dip the cloth now. When I first started, I was up in doing squash balls. Then I went down on tennis. I've done mostly everything in the factory. I get here at 5:30. I start the boiler up in the morning. Then I go on the mill and start mixing straight away. I've never played tennis, to be honest with you. No. I'll just make the balls.
Very nice they are too. But the tacky balls still need covering with a distinctive yellow cloth. And to help meet demand, the firm uses flexible teams of home workers who, unsurprisingly, do their work from home.
This part of the process is done at home by our home workers. They have a bag of balls delivered and blocks of cloth. So they start off by stripping the cloth into pieces. This cloth has got the solution around the outside. And then to cover a tennis ball, it's all about the positioning.
It's a job Louise has grown up doing, and she's not afraid to get stuck in.
I do this if we've got a late order or desperate for a ball, but generally it's just to train whoever's going to be doing it at home. We've got between 10 and 20 home workers. It varies according to what season it is, what time of year, how many balls we're making that particular month. And they get 2 deliveries a week, so there's always a constant supply.
The final stage is to seal the 2 pieces of cloth together in the finishing mould.
This cycle runs for 20 minutes. The moulds are heated up to 141 degrees. In that time, the solution around the ball melts, and then Kerry unloads them. After that, they'll be ready to be inspected, and then off they go to be packed.
Ready to be shipped off to the court. Game, set and match.